Here's another example of an improper integral of type 2, an integral that looks like an ordinary definite integral with finite bounds, but it turns out the function is discontinuous somewhere in the interval that you're integrating over. Let's find the integral from -1 to 2 of e to the x over e to the x minus 1 dx. Now, this function is actually defined when x is -1, and it's defined when x is 2. It's defined at both bounds. But there is a problem. There is a value of x that makes this function undefined. What happens if we try to find the function f of x equals e to the x over e to the x minus 1? What happens if we try and plug 0 in? F of 0, that's going to be e to the 0 over e to the 0 minus 1. Well, e to the 0 is easy. That's 1. E to the 0 again at the bottom, that's 1 minus 1. Uh-oh, that's 1 over 0. That is undefined. So our function is actually defined everywhere except at 0, and 0 is in the interval. 0 is in the closed interval from -1 to 2, which is the integral that we're integrating over. So this is an improper integral. But in order to use our definition of how to actually handle an improper integral, we need to break it up. Since 0 is not one of the bounds, we'll break this whole thing up. Let's start by splitting up this integral into two separate integrals. This is kind of like what we did in the type 1 improper integral when we had an integral going from -infinity to infinity. In that situation, we could have gotten away with not splitting it up, but here we really do need to. We need to make 0 one of the bounds of our integral so that we can actually solve it. So we'll take the integral from -1 to 0 of our function, e to the x over e to the x minus 1 dx, plus the integral from 0 to 2 of our function, e to the x over e to the x minus 1 dx. Now we have two separate improper integrals of type 2 in which the bound in each of those integrals, one of the bounds, is the problematic value, the place where the function is undefined. So now we can split this up. We can write this as two separate limits. The first one is going to be the limit as t goes to 0 from below of the integral from -1 to t of e to the x over e to the x minus 1 dx. I changed that problematic upper bound, 0, into a variable t, and now I'm going to look at the limit as t approaches 0 from below. Plus, we're going to have our new integral here. Let's pick a different variable for this. Perhaps I'll use a different variable. Maybe I'll call it s. So this is the integral from s, the letter s, not a 5, the letter s to 2 of e to the x over e to the x minus 1 dx. And we'll take the limit as s approaches 0 from above this time. So we'll need to solve both of these integrals and then compute both limits of these integrals. Now, when I look at this, I think, boy, this is already getting very complicated looking, and I haven't even begun to solve the integrals. I think I'd like to solve the integrals and get the indefinite integral, the antiderivative of this function, separately from this whole context of definite integrals with limits and all this stuff. It's going to make things very hard to read and hard to follow. Let me just pull out that integral by itself. I just want to do the steps that I need to take to find the antiderivative separately from the rest of the problem. So let's do that. Let's just find the indefinite integral of e to the x over e to the x minus 1 dx. Because, of course, finding a definite integral, the first step is to find the indefinite integral, the antiderivative, and then go from there. So let's just solve this. If I look at this, I think, well, this is number one, I can't just instantly find the antiderivative. I'll need to use some technique. The first technique we should always consider is u substitution. And that is going to work here because the denominator could be a good choice for a u. Let's let u equal e to the x minus 1. Then we'll find our du, the derivative. The derivative of this function here is just e to the x times dx. And guess what? E to the x times dx is appearing in our original integral. So that tells us that our substitution will be successful. And this is going to equal the integral of du over u. Boy, that tends to show up a lot in these kinds of problems that we solve, doesn't it? We've solved a lot of problems where we did a u substitution and ended up with a du over u. And this is an easy integral to solve. This is going to be the natural log of the absolute value of u plus a constant. We actually don't need that constant in this case because we're about to plug this right back into a definite integral. But for now, in order to be correct and complete, I'll put the constant in. All right, just need to fill in our u. This is now the natural log of the absolute value of e to the x minus 1 plus a constant. We can ask ourselves, do we need these absolute value signs? Do we know for sure that the thing inside the natural log is always positive? Or do we know for sure it's always negative, in which case the absolute value signs will negate it and make it positive? In this case, we don't know, because e to the x could be greater than 1 or less than 1. And we won't know until we know what the x is. So we need the absolute value signs because we don't know if that argument of the log is positive or negative. So this is what we've got. Let's bring this now back to our original problem. We have found the antiderivative, so we're ready to complete our integrals. So we're back to our problem here. This is now equal to the limit as t goes to 0 from below of the natural log of the absolute value of e to the x minus 1, going from -1 to t, plus the limit as s approaches 0 from above. Now again, we could have used a different variable here instead of s. We could actually have gotten away with using t here again. But I'd rather use it separate variables because they are separate limits. Just helps to make things easier to keep track of. All right, and we've got, again, the natural log of the absolute value of e to the x minus 1, evaluated at s and 2. And we'll just fill in our bounds. So this is the limit as t goes to 0 from below of the natural log of the absolute value of e to the t minus 1, just changing the variable there, minus the natural log of the absolute value of e to the -1 minus 1, that's that first part, plus the limit as s goes to 0 from above of the natural log of the absolute value of e to the 2 minus 1 minus the natural log of the absolute value of e to the s minus 1. Okay, we filled in our bounds. Don't be scared by this. This next step here is just a matter of simplifying things and evaluating those limits. That's all we need to do. In fact, it's going to be even faster than you think it's going to be. Let's give ourselves a little bit more room here and keep going. So we can work out our numerical parts here, the parts that are just plugging numbers in, or we could work out our limits. The fact is that our numerical parts here, the part, the natural log of the absolute value of e to the -1 minus 1, that's not going to simplify it down in any kind of nice way. So it's probably not worth the effort of trying to simplify it until we see what the rest of our results are. So let's ask ourselves, what is the limit as t approaches 0 from below? Well, you're going to have a natural log of the absolute value of e to the 0 minus 1. That's a little 0 minus there. We'll figure out the rest later on. So e to the 0, that's going to be 1. So we've got 1 minus 1. Absolute value of that doesn't matter. Natural log of that. So that's going to give us the natural log of 0. So what is that? Well, it helps to remember what the behavior of the natural log function is, what that function looks like. That function is the inverse of the e to the x function. The question we should be asking is, what power can I put on e to get 0? Well, the answer is there is no power we can put on e to get 0, right? This function is going to look like this. This is y equals the natural log of x. And in fact, the limit as x approaches 0 of the natural log function is actually minus infinity. So this is actually going to give us a minus infinity here for this part. So I can erase all of this junk that I just wrote down here and just write minus infinity for that limit. Minus some other stuff, but who cares? Actually, we can stop right here, because if you start adding or subtracting whole number constants to minus infinity, that doesn't change the fact that it's infinite, right? So we get minus infinity. In fact, we can stop right here and not even bother to finish the rest of the limits here. It does not matter what the rest of the limits are, because the point is, as soon as one of our limits came out to be infinity or minus infinity, we know that our integral diverges. And that is our answer. The answer is not going to be infinity or minus infinity or even a number, because the answer is this diverges. Now, if you do want to, you could actually take the time to evaluate the other limit and see what happens. In particular, ignore the constant here. The natural log of e to the 0 minus 1, again, that's going to become a 0 in here, which means we're going to have minus infinity with a negative in front of it. So that's minus infinity, which of course makes that plus infinity. You might be tempted to say, well, minus infinity plus infinity equals 0. But can you really say that? No, you cannot. Infinity minus infinity is an indeterminate form. If infinity minus infinity is appearing in one limit, what that tells you is that you're looking at some functions, a difference of two functions that are both going off to infinity at maybe different rates, and you'll need to do a bit of work to simplify the functions and simplify the function that is in that one limit to see what answer you really get. If infinity is coming out of one limit and minus infinity is coming out of a separate limit, and you try and add them together, you can't even do that much. These are two separate limits. You cannot combine them together, because if you do, all kinds of worse paradoxes arise. So do not be tempted to say that we have a minus infinity plus infinity and we get 0. It does not work that way. As soon as any of the limits in this entire process comes out to be infinite, you stop and you say, this integral diverges, and that is all that we can say about it.